What happens when you place an inflated beach ball on the surface of a pool of liquid such as water? The ball floats on top of the liquid's surface. The ball has a weight that exerts a force F weight downwards on the contact area between the ball and the liquid. Since the ball is in static equilibrium, and is clearly being supported only by the liquid beneath it, the force that is exerted from the liquid on the ball, which we will call F buoyancy, has to be equal and opposite in direction to the force due to the weight of the ball. If you were to push the beach ball down with your hand into a pool of water, until it is fully submerged within the pool, you should observe the following. The force required to keep the ball submerged, which we call F hand, increases as the submerged volume of the ball increases. Let's watch the animation again, paying close attention to F hand. And let's freeze the animation when the ball becomes completely submerged. Observe how the magnitude of F hand, which is represented by the length of the force arrow, starts out at 0, and increases as the ball is submerged in the liquid. Once the ball becomes fully submerged, the force needed to submerge the ball is constant, and independent of the depth to which the ball is submerged. So in other words, as we continue the animation, observe that the magnitude of F hand remains constant, as the ball is submerged deeper into the liquid. Finally, the level of the water in the pool should rise in proportion to the volume of the ball that is submerged underwater. When the ball is in equilibrium while being pushed downwards by your hand, the buoyancy force should be equal to the weight of the ball, plus the force exerted by your hand on the ball. You can press the play/pause button to repeat the animation, or the stop button to reset it, or drag the slider bar to change the ball's depth. When you wish to continue with the lecture, please press the play button at the top. According to Archimedes' principle, a body that is fully or partially submerged in a fluid experiences a buoyancy force that acts in the opposite direction of gravity, and is equal in magnitude to the weight of the displaced fluid. We can prove Archimedes' principle experimentally, by verifying that the tension force in the string that is holding up a brick that is fully submerged in a liquid is equal to the weight of the brick, minus the buoyancy force. The buoyancy force as stated by Archimedes' principle, is equal to the weight of the displaced fluid, or in other words, is equal to the density of the liquid, times the gravitational acceleration, times the volume of fluid displaced by the brick. For a submerged brick, the volume of fluid displaced by the object is equal to the volume of the brick. And so F buoyancy is equal to rho Fg times the brick's volume. We can thus verify Archimedes' principle experimentally, by measuring the weight of the brick, and the tension force in the string that is holding it. And then we can verify that the buoyancy force, which is equal to the force due to the weight of the brick, minus the tension force in the string, is indeed equal to rho Fg object. We can also use what we have learned about how the pressure in a fluid changes with depth, to calculate the value of the buoyancy force. See the shown link to review the pressure versus depth section. We first note that the forces on the right and left sides of the brick cancel out, since they are equal in magnitude and opposite in direction. Similarly, the force on the front and back surfaces of the brick also cancel out. The force on the top face of the brick is equal to the pressure at the top face of the brick times the surface area of the top face. Pressure at the top can be written as rho Fg times capital H. The direction of this force is downwards, perpendicularly to the top face of the brick. The force on the bottom face of the brick is equal to the pressure at the bottom face of the brick times the surface area of the bottom face. Pressure at the bottom can be written as rho Fg times capital H plus lowercase h. The direction of this force is upwards perpendicularly to the bottom face of the brick. The net buoyancy force, Fb, can be calculated as the difference between the pressure force at the bottom of the brick and the pressure force at the top of the brick. We can simplify the expression for the buoyancy force by substituting the expression for F bottom and for F top. Noting that the top and bottom surface areas of the brick are equal, we get that the buoyancy force is equal to the density of the fluid times the gravitational acceleration times the height times the surface area of the top or bottom face of the brick. Since the volume of the displaced fluid is equal to the volume of the brick, and both are equal to HA, we get that the buoyancy force is equal to the density of the fluid times the gravitational acceleration times the volume of the brick. This is equal to the weight of the fluid that was displaced by the brick, as stated by Archimedes' principle. The buoyancy force acts at the center of gravity of the displaced fluid volume. If we replace the brick by a plastic block, we observe that the block floats on the surface of the liquid. In other words, the block is not fully submerged. Since the block is in static equilibrium, the buoyancy force is still equal to the weight of the block. In this case, the only difference from the previous derivation is that the gauge pressure at the top surface of the block becomes zero. Hence the buoyancy force in this case is equal to the weight of the volume of fluid that is displaced by the submerged portion of the block. For an object that is not box-shaped, like the object shown here, the net buoyancy force would need to be obtained by integrating the pressure times the area over the entire surface of the object. But we would still arrive at the same result, which is that the buoyancy force is equal to the weight of the fluid that is displaced by the object. For a floating object, like the block shown here, the force due to gravity that tends to pull it down is balanced by the buoyancy force that tends to float it up. As we have seen before, the buoyancy force is equal to the weight of the displaced fluid, or the fluid density, times the gravitational acceleration g, times the volume of the displaced fluid. The force due to gravity's pull on the object is equal to the object's density, times g, times the object's total volume. By setting the FB equation equal to the FW equation, and cancelling out g from both sides of the equation, and then rearranging the terms, we can get the shown equation for the density ratio. The density ratio, as it relates to buoyancy, refers to the ratio of the density of an object that is placed into a given fluid to the fluid's density, and this is equal to the ratio of the displaced fluid volume to the object's total volume. Let's examine the table shown here. When the density ratio is less than 1, the object's density is less than the fluid's density. This means that the object's total volume has to be larger than the displaced fluid volume. Hence the object floats on top of the fluid, with part of the object's volume outside of the fluid. When the density ratio is equal to 1, the object's density is equal to the fluid's density. This means that the object's volume has to be equal to the displaced fluid volume. Hence the object is neutrally buoyant, and can hover at any depth within the fluid, while being fully submerged within the fluid. When the density ratio is larger than 1, the assumption of a floating object is no longer valid, and the buoyancy force is no longer equal to the gravity force that is acting on the object. In this case, the object sinks into the fluid. When the object reaches the bottom of the fluid's container, the reaction force from the bottom surface plus the buoyancy force are equal to the gravity force on the object. Here's the same object that we've seen before, placed in a fluid. You can use the slider bar to change the density ratio. Then observe how this changes the way in which the object floats within the fluid. Notice that at a density ratio equal to 1, the object can hover at any depth within the fluid. When you wish to continue with the lecture, please press the play button at the top.